Good morning. My name is Bob Armstrong, and it's my pleasure to welcome you to this special MIGHTY seminar. The MIT Energy Initiative has been working during this COVID crisis to bring lots of new and interesting content to the MIT and broader community related to the energy and climate challenges. And it's a pleasure to have with us today Dr. Dirk Smit, who's Vice President of Research Strategy at Shell, to talk about challenges and opportunities in net zero emissions energy systems. As I mentioned, Dirk is VP of Research Strategy at Shell. He's also chairman of Shell's Science Council and chief scientist in geophysics at Shell. He's got his PhD from Utrecht University in 1989, doing a PhD in mathematical physics, specifically studying string theory. He's gone on to do postdocs at Berkeley, Harvard, and joined Shell's geophysics R&D group in the Netherlands in 1992. He's held a wide variety of positions since then at Shell, but I think it's fair to say he's viewed as one of the leading visionaries with regards to science and Shell's future. And I think he's always got interesting things to say about science and its implications for the energy sector. I know I certainly always come out of conversations with Dirk with new insights. He holds a number of positions outside of Shell. He's on the MIT MIGHTY External Advisory Board, the MIT Advisory Board for the Earth, Atmospheric and Planetary Sciences Department. He's a fellow in the EAPS ERL, Earth Research Laboratory, and holds a number of visiting professorships around the world. It's again a real pleasure to have Dirk with us to talk about challenges and opportunities. I'll just make a brief comment that since earlier this week, there were a number of releases about Shell's new business plans headed towards a net zero future by 2050. That this talk was put together, designed well before that came out, and this is a science and technology focused talk. I have asked Dirk, and he's certainly willing to come back later and talk more about the business implications of these kinds of ideas. But for this morning, I think we'd like to focus on science and technology and its implications for how do we get to net zero. So with that, let me turn it over to Dirk for your presentation.
Well, thank you, Bob, and thank you for your invitation and kind words. I first would like to check, am I audible? Can you hear me okay? And can you see my slides? Okay.
Hear you fine, yep. You're
okay.
Good.
So, indeed, I had a bit of a thought of why I would use the word challenge in there, because these are challenging times, as we all know. And it's easy to sort of be put off by yet another challenge and actually come away a bit gloomy. That's not my intent at all. I do think there is a fantastic future ahead of us, in particular in energy systems that are net zero emissions. So in my view, the future is bright. If anything, I hope that this talk will give you some insights of why that brightness may be there. Before I do that, a bit of a downer perhaps. Don't read this, but this is, I need to show this to remind you that I work for a publicly listed company. And you shouldn't actually buy or sell any stock based on my talk here today. I don't know why it takes that much text to explain that, but that's what this is. I also am realizing that, yeah, you may have other things to do and also occasionally wander out to other things that happen in your vicinity and at home or wherever you are. So I thought I might as well just start with what my main message is, and then hopefully trigger some interest, or at least make sure that you get that message. There are 4 takeaway points at least, that I would like to make sure we can discuss. The first thing is that a net zero emission system is different from a 100% system, a system that we probably have today, or at least close to 100%, where fossil hydrocarbons are by far the dominant energy carrier. A net zero emission energy system, by contrast, will consist of many more, or at least a few energy carriers. Maybe some of them may be much larger than others, but there will be not that much larger. And what is important in order to get to net zero emissions, the actual composition will include low power density renewables, and maybe also high power density energy carriers, for example, like nuclear, and that is relative to fossil hydrocarbons. What is also important is that you realize if you have more carriers or more legal blocks to play with, then more conversions are also possible. And what is perhaps different from, let's say, a few decades ago, is that we understand how these conversions may become very efficient thanks to new technologies and new advances in material science. And hence, what may very well happen over time is that we become very good in such energy systems to highly optimize solutions and specific uses for specific markets in energy sectors. So in other words, this wholesale supply model of a one size fits all may actually not be the dominant thing on how to actually address markets or user groups of energy. This highly optimization is made possible by a lot of advanced technologies. A second takeaway is that, and that has to do with something that I will spend quite some time on, is that large scale penetration of different energy carriers will depend on their environmental footprint. And that means that you will not get to a 100% solution very quickly if you insist on a net zero emission energy system. That may sound a bit counterintuitive, but hold on for a moment, for some time and during this talk. And hence there will be trade-offs. Trade-offs exactly at the point where people start to get interested in perhaps other systems of energy supply. And in a net zero emission system, with lots of renewables, a very important condition comes from land use. And that is perhaps also counterintuitive, because many people compare, say, the capacity factor of a solar panel with this area of a particular country and conclude that there's plenty of space. We'll actually demonstrate that is actually much more nuanced. A second trade-off may actually occur by the mining that may be needed. I won't have much time to discuss that, but mining as an effort to build the infrastructure for solar and wind, in particular the energy capturing, as well as the storage devices that may be needed for that, may take up a lot of material. These two things will mostly be important in Asia, where most of the growth of the energy system will be. A third point that I will realize is touching upon the fact that Asia indeed is important, is that different regions will realize net zero emissions differently. And that may depend on geographic differences. Economic development is very important, and also cultural and political considerations. Much less so perhaps by technology itself. And that's where I will start part of my talk. So where the trade-offs actually are decided and how to go about them, and hence what the priorities may be for Asia and Africa being mostly concerned with economies that are still in their development stages, as opposed, say, perhaps to the US and Europe, priorities may really be different. And not only that, there may also be new energy sectors growing because of parts of the trade-offs, including mining, as I mentioned already, but also, for example, desalination industries to cope with a lot of fresh water production. So hence, in a net zero emission system, we do see a large degree of difference, say, amongst different regions. What is very important to make a net zero emission system work is a degree of circularity, or at least of intra-sector connectedness, where a sector is, say, an industrial sector, or at least a market sector in energy. And to be absolutely short, it's a little exaggerated and is not factually really true in that sense. But you could think of this as one sector's waste becomes another sector's resource. And I will show you an important example, in my view, a very large example, where agricultural optimization and agricultural technologies and energies start to become very intertwined with the structure or the fabric of a net zero emission system in Asia, and say, or in tropical countries to begin with. And then there are a few underlying challenges that I'd like to address. I will not be able to do this in any way of comprehensiveness, but the most important ones that are probably true for most net zero energy or emission systems, in other words, true for most regions, we'll have to really think about how large scale energy resource storage may occur both on site as well as through grids, or for that matter, really large scale, more of a strategic relevance to a country or a region, including CCS. I mentioned already agricultural optimization in conjunction, for example, with decarbonization of manufacturing industries, but also around hydrogen. Hydrogen as an energy system. It's not only a fuel, it's also a carrier and storage, and in that sense, and it is very relevant in a net zero system because you can make it really carbon free. So those are four things that I'd like perhaps to ask you to keep in the back of your mind as we go through the talk. So how I will do this, I will introduce those four topics, is that I will start with a few observations on the current energy transition, and I will do so that through a Shell lens. And I don't do this just to sort of moan and complain about the fact that, well, we have to give up hydrocarbons. It's mostly through what Shell actually brings in this discussion in terms of scale and insights of how energy systems actually work. And then I will introduce a concept that's not new, but I do think it's sometimes a bit overlooked or dismissed even in important discussions on how net ZEs may be designed, and that is power densities. And then I will actually be able to show that NZEs are largely shaped by societal and economic aspects, and then indeed enabled by technologies further, not the other way around. And then I will actually make a specific case for Asia, and in particular India and China, where I will show that it is likely, I cannot predict, and hence I don't want to predict either, but I'll make a case that it could very well be that different priorities will be set in those countries or those areas. And as a result, I will touch upon some of the grand challenges that I just discussed a minute ago. So I said that I would start this talk by starting by looking at an energy transition that we currently see through a Shell lens. Well, if anything, as anyone may have seen, what Shell has announced, we have accelerated our Shell's climate ambition at the start of the COVID, once we realized that this is the opportunity to really sort of start accelerating efforts that were already in place. And at the middle on this slide, you see that we strive to get a net zero emission energy business by 2050 or sooner. And that 2050 or sooner should be seen in the context of what societal developments or regional developments in different societies actually lead to. It consists of three parts. We first, of course, have a net carbon footprint ambition around 1.5 degrees, which is consistent with this net zero emissions by 2050. We then split this out by making our own operations net zero emissions, and we partner with clients, future clients and existing clients, markets, where we partner for decarbonization. In other words, help people to get off, say, emissions of CO2 in the atmosphere in their efforts to use energy. And in that sense, they may become indeed clients of us. This is at the heart of what I think was put out at last week or earlier this week by Shell, and built on that, business strategies are developed. And as Bob already said, I'm actually not talking about so much what the actual business decisions are here. Maybe some of them become clear. I mostly would like to actually highlight some of the underpinnings in that thinking, which is mostly around technical and scientific insights that played a significant role. I think from a Shell lens, what people may not realize so much, it's not so much that we actually change hydrocarbons for something else. It's the fact that a large part of Shell's business, when dealing with in oil and gas, is based on getting access to the right geology. And the right geology, as we all know, is not uniformly distributed. The right geology is, in fact, quite unevenly distributed. And To find what the right geology is, we need a lot of technologies to find that out in imaging of seismic data, and then of course in how to actually then deal with the subsurface risk that is remaining in these images. These images are never pictures of the subsurface, they're actually highly noisy impressions of what might be down below. But in actual fact, whatever technology, whatever imaging is, if you're in the wrong block, you're not going to get very far. And in fact, it's even worse. You should be in the super blocks in any basin to really make a significant business out of this. Second tier, third tier blocks, no matter how good your technology is essentially also, yeah, a bit of a slug, if you wish. In contrast, if we move into a net zero emission system, it consists of many more energy carriers and carriers that are let's say renewable carriers, solar and wind, say, and the game actually becomes really different, because the actual carrier itself may be produced almost everywhere and also may be produced very cheaply. It may not be such a technology game per se, or it certainly is not determined by access so much. It's mostly determined by access to technology. And that technology also features in something else. We need to get much more smarter about how do we build systems of these different carriers and conversions. I alluded to that already in my main message slide, that those are actually quite crucial, because that's where people will make optimizations and will make choices and priorities while still aiming for net zero emissions. So it becomes a technology game, and as a result, access to technology becomes a lot more important, and maybe less, although it may come back with a bit of a vengeance if you're not careful, as I will show you later, access in terms of favorable countries or areas in the world to like similar we have with accessing favorable geology is less of an issue. It's more about systems engineering and complex multifaceted systems optimized to client groups and markets, but based on carriers that are essentially available everywhere. And that is a huge change. That is a huge cultural change, and that's also a huge change that is sometimes less realized. It also shows where Shell's strength actually is, because it's not true that we don't know these systems in a geology-driven world. In fact, most of the supply systems and energy systems to actually bring, say, hydrocarbon energy to an end user are very complex systems involving a lot of transport, supply chain, and generation, storage, etc. All that is optimized fully into very large scale systems. That knowledge is deeply embedded in most Shell's engineering and business groups, and will come now again seen as very important as we start to build a net zero emission energy systems at scale. So that part remains, and that is essentially, say, part of the message in this slide, apart from the fact that culturally there's a huge change happening in companies like Shell. It's very clear already for some time in Shell that low carbon and renewable energy solutions for Shell would mean two things. One is an investment or a focus on clean and green power generation, because electricity is, of course, the name of the game. In order to get to net zero emissions, a significant amount of electrification will need to happen, or it would at least be very advantageous to have that, much more than we currently do at 20-25%, maybe up to 50%. And on the other hand, there are a number of other fuels, if you wish, or energy generators that may in fact become very important in such a role, but again, may not be sort of universally available, maybe with the exception of hydrogen, but also biofuels, biotechnology, synthetic hydrocarbons. You may have seen the press that Shell was able to produce recently 500 liters of synthetic kerosene that was used in a plane by KLM flying from Amsterdam to Schiphol. Of course, that's only a very small amount of the actual kerosene that is needed, but at least a start has been made. And these synthetic hydrocarbons used in, or kerosene, was actually only made by CO2 coming out of a waste stream out of industry, our own refineries, and hydrogen. And there may be more, maybe others. But those two are essentially two aspects of what the net zero emission energy business in future may probably look like for Shell. As I said, I cannot stress enough the role for hydrogen. It's not only perhaps a fuel, it's also a base chemical, if you wish, or a base agent to build large systems from. Large systems from in terms of storage, or indeed of also in different markets, it will play its role. It plays a role as a fuel. It may also play as a base chemical at the root of a more green chemistry, if you wish. It may also be at the root of the circular argument that I mentioned before, in terms of turning waste of some sector into a usable product somewhere else. And that has to do with the fact that a lot of this waste actually can be combined with hydrogen into processes we actually know, maybe not at scale yet, but we do know them, to actually make something useful out of that. And in fact, this synthetic hydrogen that synthetic fuel that I just mentioned is an example of that. And hence systems engineering, apart from just the production of hydrogen and then the trading perhaps in hydrogen, both as a resource as well as a carrier, is actually something that will be very attractive to large-scale energy companies. Now I'd like to change tack, because we know that energy so far in humankind, history of humankind, has done great wonders or great things. In fact, there is a strong correlation that human development and human quality of life, if you wish, income, etc., is very correlated with the consumption of energy per capita. And what you see in this plot is this correlation. I don't know whether you could see my mouse, but I hope you can. You see on the left, countries that are still in stages in developing their economies. And on the right, you see, in fact, countries that you would argue are living in advanced economic stages of their development. And indeed, also the Human Development Index as computed by the United Nations is indeed a lot higher. The question is, of course, whether you would actually increase this, because world population is growing. It's by far not a given that the current energy system can just be extrapolated, even if that were an option to begin with, let alone that a net zero emission energy system would continue this drive that everyone has as an individual, that you would like to improve your life. And hence a large part of that may be about having access to energy. In fact, I'd like to take you back to what actually happened around the Industrial Revolution in England in the 18th century, around 70, 80 or 90. Technically speaking, it started perhaps at 70, 60, but what I'm saying is relevant only 20, 30 years later. And what I'd like to get back to you is a theory that sometimes is a bit controversial, because many people did many things with this, but I would like to use it in its purest form as it was originally formulated by Thomas Malthus, a British economist and philosopher, who actually argued that a lot of mankind, in fact, all of humankind, before, say, the Industrial Revolution, was essentially trapped economically in what was later called a Malthusian trap, where in fact population growth would be fundamentally exponential or close to exponential, and whether the resource additions or resources growth, like food, but also other means vital functions to sustain life or to make a living, actually would grow linearly or at best polynomially. Well, every mathematician will then realize that there is a point at which the exponential curve will overtake, say, the growth of resources, and at that point the income will essentially get redistributed over the larger population. So a Malthusian trap is essentially, at the end of the day, just simply a DC shift. It's a DC shift in the fact that the income that you had prior, perhaps to some technical breakthrough that would allow you to create more food or to create more energy or to create more material or other devices, say, if that doesn't really grow fast enough, then it will actually be taken up by a growing population, and hence lead to the same situation as before, except for the fact that there are now more people. That didn't happen at the Industrial Revolution. What didn't happen there was not so much that there was all of a sudden a lot more technology, which is true, But what also happened then is that that technology actually fell in a very fertile ground, namely in a society that was already emerging as a middle-class society. There are long stories, and I would refer to you to Gregory Clark and Hamilton, who wrote about this very recently, in fact, and a number of papers on this. It actually showed it was not so much the technology per se that led to the enormous wealth increase, in fact, a wealth explosion made possible by the Industrial Revolution that actually outpaced, say, the growth in population. Because of a cultural or a societal phenomenon, namely that the emerging classes, the emerging middle classes were already quite large when the Industrial Revolution started to happen. If it weren't for that, the thesis is that it probably would not have gone as so far or so spectacularly successful. And further on, what happened as well, as we know, is that most of the extra wealth was actually happening in manufacturing jobs that didn't exist because of that technology not being there, and that could scale up in particular because of this middle class culture. Now, eventually, as we know, it's much more advanced societies, and the exponential manufacturing actually stops, and maybe more service industries and efficiencies and circularity. You could argue maybe we are closer around this point in the US and in Europe, at which point, say, the quality of life will still increase, but is not so much coupled anymore with high energy intensities that are needed to actually power all this manufacturing. Keep this picture in mind, or this concept in mind, because if we now look at where others may actually then grow into something that you could call could be an industrial similar effect as this industrial revolution, then it will be in middle class, the rising of the middle class in Asia. And in fact, many people may realize this already before. I found it actually quite insightful that the size of the middle class in Asia is not only growing as fast because of technology and the wealth that may be created by this technology in an already large middle class, or at least a middle class that is large enough, but going forward, by 2050, about 3 billion people will grow into the middle classes from what you could argue is still sort of the poverty regimes, the people living in extreme poverty sometimes, or maybe not even so extreme, but nevertheless are not part of the middle class. And already by 2030 is about 1.5 billion. And most of these people will start to work in manufacturing industries, as we know. That actually implies that, say, at the time frame that Paris is relevant, we need to be worried about the fact that these highly intense energy consuming industries will also be emitting quite a lot of emissions because they're not green. They basically burn on coal. And maybe there are advances there soon, but still it's quite mostly done by coal. And already 50% of the greenhouse gas emissions come from Asia, and China is already responsible, I think, for 28%. What is interesting, if you look at how that manufacturing actually clusters, is to look at the graphs here on the right. You see here the annual CO2 consumptions here at the top, say here in China, which is about 1 billion ton larger in 2019 than the actual consumption for the Chinese economy itself, for a Chinese, would you allowed to believe, or would be needed. So in other words, there is a lot of manufacturing happening likely that for goods that are exported. I cannot prove this just on these two graphs, but it's very interesting to see that on the US side, for example, we see quite the opposite, where the consumption-based CO2 emissions would be larger than, in fact, or are larger than what the annual CO2 emissions actually are. In other words, someone else builds, say, the CO2 or burns the CO2 into the atmosphere from manufacturing somewhere else. And so maybe this is indeed a proof, or at least an indication that some offshoring and onshoring is happening. But for the climate problem, that doesn't bode very well, because it might very well be that manufacturing in the US at the time was probably already more on gas-based and maybe cleaner, than perhaps initially, at least, it was in China, where these things start to grow, still burning on coal. Those are things, therefore, that we need to consider when we start to study, well, what actually may happen in China and how, say, energy choices will be made towards a net zero emission, as China has also committed itself to. Something else that's important is that when you start to build economies that are seeing a lot of jobs occurring in or appearing in manufacturing, then people start to live in cities. Indeed, when the population on the vertical axis, you see the population living in urban areas, and predominantly the more developed economically, people live indeed more in cities and also are indeed much richer. There's a good reason for that, because manufacturing is most easily done in concentrated sites, and these concentrated sites attract a lot of people. And if you now would like to make use of services that you probably cannot afford immediately if you come to a city, then yeah, you might as well you work or live very close to each other, simply because you can then share some of the buses, etc., and some of the infrastructure. And hence cities are by nature, say, occurring simply because of this drive of manufacturing jobs in centralized positions, in centralized areas. And that has a big consequence for how to arrange an energy system. If it's left to its own devices, then what happens is that people naturally will go to energy choices that are, through technology, able to become accessible as a result. Manufacturing industries occur that can be actually done at sites of big factories. But in actual fact, what compared, say, to sustenance farming, the energy density, but more importantly, the power density, which is what you see here on these diagonal lines, increasing from very low to much higher, actually starts to increase. And in particular, societies that are early in their economy and are breaking out from this Malthusian trap to lift themselves out of poverty are very well helped by high power density resources, because that's easy to deal with in a city. And essentially, a lot of the growth may actually be determined by how easy access you have for energy systems that optimize, say, on power densities. And that's, I think, an important insight that already is listed by David Mackay, who unfortunately no longer lives, but wrote that down in a book, Sustainable Energy Without the Hot Air, back in 2009. Sometimes we tend to forget these things, because if you make a plot of where actually are the producing areas of energy carriers of energy that we use, with respect to their power density, so how much power density is needed to actually create these energies versus where we use them, which is depicted here in red, then you clearly see that most of the production of the conventional systems actually are more or less in line or on the same area or slightly above of where we actually use these power densities. Even whole cities you can actually assign to a power density. And unfortunately, a lot of the renewables or other, with the exception perhaps of nuclear energy carriers that you bring into this system to become net zero emissions, do face a challenge that you are generating them over much larger amounts of land or sea, and actually need to work that up by whatever system you can design for that in order to work in industries, because people do live in cities already. And as I just showed you, they live predominantly in cities in developed economies. And they're starting to grow, these cities, in Asia, mega cities indeed, even much larger and with much more dense population densities in Asia than, for example, in the West. And to give you just an example to that, this is the city of Tokyo. You can just calculate, and I'm not suggesting here that this calculation is actually very relevant in its detail, because it may change. The sums are not so difficult to make. But the power densities of Tokyo's business units, for example, are around 500 watts per square meter to 1,000 watts per square meter. It's very similar to what New York has. And this is in a developed economy, as we all know. If you now start to wonder, well, look, let's see whether all the electricity that we currently use in Tokyo can be taken up by solar PV, then a quick calculation actually shows you that you need an awful lot of land to actually store or to build solar power. And whereas the actual surface area of Japan is way larger than what you would need here for Tokyo. But the actual fact is that the land around Tokyo, up to 1,000 kilometers, is actually used. It's either forest in hilly country and not very conducive to build large amounts of solar because you need to kill all the forest, or it is actually used for agriculture or water resource management or other functions that are needed to indeed sustain a significant group of people, about 39 million. And if you add to this the need to storage, then even say for a 2-day storage of, let's say, a significant part of 50% or a significant part of solar energy to be used here in Tokyo would actually create an enormous amount of storage that is needed. And it's not very clear that Tesla batteries or Tesla Powerwalls will be able to do that, if only because of the enormous cost. There's another area that comes into play here. This amount of solar panels for just the city of Tokyo, never mind all the other big mega centers that occur when the middle classes actually start to grow around the globe, will need a lot of building or a lot of material to do this. And indeed, some calculations actually show that the mining may need to improve about tenfold. And mind you, this is an industry, the mining industry, that already in its oil consumption is very similar to the actual aviation industry before the great lockdowns. And this is something that that actually should worry you then. How to decarbonize this if they're so dependent, say, on building, say, solar and wind devices. So we need non-chemical storage techniques to at least alleviate perhaps the storage amount. But the ones that we know, like pumped hydro, actually have very low power densities. And in fact, I live in a country that is exactly flat as a pancake. There's not a whole lot of pumped hydro possible in this country. So we need something else if you would like to do this. And you could argue that the whole of the Netherlands is a very densely populated area. It's only less dense than Bangladesh at the moment and uses a lot of energy. So this is not a panacea, and in fact, it will only get worse. This is the current situation where people live, and you can see in red that mostly people live in large areas, urbanized areas in Asia already, and this will only start to grow further if indeed these middle classes start to become sizable and essentially start to work in jobs that most likely will create an even larger amount of manufacturing, if only for their own societies, let alone that they may be concentrating manufacturing for the rest of the world. Now, there is some relief, I would say, and that is not something that people often realize. They do claim, though, that leapfrogging may happen. In other words, we can teach, say, developed economies can maybe teach developing economies. I would argue we need to be very careful with that because, as I said, the actual success of economic development enabled, say, by technology is largely driven by a cultural aspect of the middle classes that need to grow, and is much less perhaps dependent on technology that needs to be imported. The technologies will be developed because people will make different choices based on how they would build their cities and on geography, as we said, the amount of land that may be needed, etc. But it is true that if you look at the GDP growth versus the amount of energy that is needed for a certain amount of economic development, if that may say so, and this guy here, Vetter, actually wrote a paper on that, on how to normalize this in a consistent and meaningful way, then the flatter this curve, for example, China, means that there is less energy needed for the same economic output as perhaps a developed, fully developed economy, Japan, had to do when it went through its developments of growing the middle class into what we currently see as a fully developed economy. So the fact that this is flatter means that perhaps it's more efficient. Maybe digital technologies have something to do with this, and this is certainly something that I would argue we need to look at carefully. So what does this mean very briefly then? Well, introducing NZEs or net zero emissions, we need to focus on large urban areas, mostly on monsoonal Asia. Because that's where most of the burning happens, and that's also where most of the growth of the energy happens, and that's also where most of the climate problem probably will need to be solved. As I said already, the NZEs are inherently consisting of several energy carriers, and what choices people will make, for example, in Asia, may actually depend very much on the land availability, the amount of economic development, and perhaps also the degree of independence that people would like to achieve. For example, a country like India is hugely dependent on its energy from outside India right now, but the sun is shining in India quite well. So a lot of pressure is to build, of course, solar panels in India, but it may need to be offset at some point, simply because cities in India tend to be even denser than Tokyo. And that means that natural gas with CCS, or as I will show you in a minute, advanced nuclear reactors may actually become quite reasonable options for countries in Asia and maybe later on in Africa. What is also true is that a large part of any, say, decarbonization that will happen in Asia equally, may actually be helped with a significant switch to hydrogen as soon as we can. And that actually means two things. We need to be able to produce it in clean ways. We also need to be able to build hydrogen uses further next to electricity, perhaps. And as I said, a lot of the electricity supplied in clean ways requires a lot of mining. So there may be a pressure building here, or at least a trade-off point. And that will be for different regions in different ways. I will now actually go to discuss very briefly 3 challenges and opportunities where I think from a technology and science point of view, we might want to look more closer to. One is the actual route to power. There may be many more routes to power than just one. And in particular, not to suggest for a minute that Shell is actually building a nuclear business, not at all. But we are interested in participating in studies to see how it is happening, in particular in relation to hydrogen. I will also stress the need for non-chemical energy use, mainly because I'm not so worried about the fact that batteries will become a lot cheaper and hence can take over, but it's the sheer material pressure that will be in there. And hence other non-chemical ways of storing energy may actually be attractive as well. And then, as I said, it becomes really important to understand very early on what are the options to connect the different sectors in an emerging net zero emission system, even while you're still, say, burning a lot of hydrocarbons, say, to figure out where are really the opportunities to connect and actually build some degree of circularity in there. And in a context of Asia, I would say that comes mostly from coupling it with agriculture. Very briefly, I got these slides from Jacopo Buongiorno, who may in fact be in the audience. And I'm actually part of an advanced expert group on nuclear production that looks at advancing nuclear batteries. These batteries are very small, are not like at all light water reactors of 2 gigawatts. These things are much smaller. Maybe there's an SMR version that actually gets a little larger, let's say up to 100 megawatt. But the essence is that you can build them in a factory, and in a factory. If you allow me, Bob, for another 5 minutes, then I'll be done. And hence they come with significant attractiveness in the fact that you can seal them off in a containerized plant, build them in a factory and dispatch them to a client. Obviously, the power density is much higher than wind or solar. What is interesting is when you start to optimize that with an electrolyzer. Most electrolyzers for solar and wind, there are 2 versions, the proton electrolyte membrane, the PEM, as well as the alkaline. They operate, of course, at room temperature. But with the advantage of having a nuclear generator, you can actually have them working. These are different concepts, of course, at higher elevated temperatures. And then the efficiency of actually splitting water becomes a lot more. It's in general about 30 to 40% more efficient. And in fact, there are studies now where people build as part of the DOE programs to build next to existing nuclear power plants, so not the batteries that I just talked to see how that may work in terms of hydrogen production. And in fact, there's reason to believe that those routes to absolutely zero carbon hydrogen are quite competitive with, for example, steam methane reforming plus CCS at a significant amount of tax credit or tax burden for CCS around $150 a ton. People may say, well, that's way too much. Well, in fact, in California, I think the actual subsidies for CCS is even higher than $150 a ton. So what I'm saying is that give this another 10 years, and it may very well be that routes to zero carbon hydrogen may actually be available. Whether that's acceptable in a society depends on many other things. But certainly in Asia, with a lot of land already used and where significant reforms need to happen in land management anyway, these may be for dense cities like Shanghai or Mumbai. In fact, quite attractive solutions, and it may very well be, given the amount of investments that the Chinese and Indian governments do already next to solar and wind in, for example, small modular reactors as well as nuclear small micro reactors, is actually quite significant and growing. It's growing quite steeply. I mentioned the need for CCS. CCS is not just storing things in the subsurface. In fact, it's a complete system that needs to be lifted to scale. The challenge, however, is for this to work, the actual capture technology needs to go up in its effectiveness. Its effectiveness of 90% is not enough. It needs to go up to 95, maybe to 98% to be really a solution at scale for a net zero emission system. And then you can couple that, if you store it into the subsurface, then obviously you can actually take advantage of geothermal aspects. And if you store it, for example, in a saline aquifer, there's work by Martin Saar at the ETH in Switzerland, as well as in our own shop in Shell, to see whether that kind of storage of CO2 in saline aquifers that are deep 3.5 kilometers may actually be used in a simple energy storage system, at which now supercritical CO2 is the working fluid. And that working fluid is very attractive because it is close to its critical point, and hence acts really more as a fluid than as a gas, and hence the turbines may be a lot smaller. This is something that people realized also, for example, in Net Power, when they start to build the Alum cycle, which runs entirely on CO2. And hence, it may very well be that CO2 as a working fluid, maybe in combination of future geothermal applications as part of CCS operations, become attractive and maybe a key to scale. That will not happen everywhere in every region, but it may be happening, for example, in Texas, in the coastal waters of Texas, and maybe also around the North Sea, and maybe the South China Sea, where in fact a lot of people are already used to offshore engineering for oil and gas. And then I'd like to touch upon something, a non-chemical storage measurement in addition to CCS, which is really an idea around isothermally compressing and decompressing air that you store in cylinders, maybe 20 meters at the deep sea floor, let's say at 2 kilometers. This is actually leveraging a lot of capabilities in the oil and gas sector. And it's astonishing to see that actually quite quickly you can get to storage power densities that are rivaling hydrocarbons. And these techniques to put things on the seafloor are not so uncommon. We deploy a lot of seismic sensors, for example, on the seafloor, in fact, in deeper water than this. And just look at the numbers. This is work we're doing with Phil Lubin at the UC Santa Barbara. That's 40 terawatt hours. So this becomes really sort of perhaps strategically relevant non-chemical storages for cities that are completely off the grid, or at least off, say, hydrocarbons and fully powered by renewables. And then I said something about agriculture. I don't have a lot of time for this. I'm running out of time for that. Agriculture needs to go through a significant innovation or densification if, say, 10 billion people need to be fed, and mostly, say, in areas like in Asia. And it's already quite a challenge to do this with current technologies, with current energy densities, let alone that you would like to decarbonize the agricultural sector. But maybe there's help from what you could argue are novel insights. This is a science that really looks at enriching the soil with CRISPR technologies, as well as with biochemical pathways to actually see whether plants can take up a lot more CO2. Biodiversity plays a significant role into this. So it's not at all a fertilizer game per se, but it is perhaps optimizing the topsoil to not only get a much more denser production in terms of crop yield, but also a denser uptake for longer periods of time for CO2 by the topsoil. And as most people know, in fact, by the short carbon cycle through the topsoils, about 70 gigatons of CO2 is converted into plant and biomass. Unfortunately, it also gets released, say at the end of a harvest season, etc. We can start to tinker with these two very large numbers that are subtracted, say, leaving a net storage of CO2. And there is now indeed in the critical zone, as people would call it, signs emerging that actually holds great promise. Why do I show this? Well, it's particularly relevant in the tropics, where carbon content in the soil is not as high as in northern latitudes. And is one of the reasons that the World Resource Institute has identified is a reason why, say, fertility in the soils in the tropics is indeed less. I'm not a farmer, or for that matter, an agricultural expert. And I'm also not suggesting that Shell will step into this, but Shell may have something to do with this. In, say, decarbonizing, for example, heavy industries and essentially getting access to, or in our own industries, for example, having access to significant amounts of CO2 in concentrated form, and essentially through an oxalic acid and an ester processing, creating hydrogels that may actually condition the soil such that a large amount of CO2 and other resources may be much more optimally distributed and managed in a soil to be conducive for a lot more CO2 uptake, as well as more, and most importantly, growth for food in these areas. So you start to see that optimizations and the need to decarbonize in an agricultural setting may have, say, things in common that normally probably will never meet or never be surfacing with decarbonization's efforts in heavy industries, or for that matter in transport. And as a result of this, a chemical industry that actually looks at biodiversity or at biochemical pathways to produce things like these hydrogels, for example, that you do in Shell, or experimenting with that in Shell, as several other groups do as well, may actually hold great promise to start to build this degree of circularity. And you're talking large amounts of CO2. It's not small. You need to improve the soil over a significant continent, in fact. So let me conclude with my main message. I will not read it out again, but suffice to say that net zero emission energy systems are a lot more fun, if you wish, from a technical point of view, because there are many more legal blocks to play with. And from a business point of view, it actually holds great promise, because in a customer-centric way, away perhaps from a wholesale supply model, there are many more clients and client groups or markets accessible by highly optimized uses and production, thanks to technology. I think that in every net zero emission system, there will not be 100% solution, and hence there will be trade-offs necessarily with competing energy carriers and energy generators, as well as energy uses, determined by, as I try to explain more, by cultural and economic factors perhaps, and geographies, whether you have mountains or not, for example, then perhaps by the technology per se. And that is actually something that people should bear in mind when you start to go about the world or the globe to see, well, what would work where. What is very important is that in most of these net zero energy emission systems, this degree of circularity needs to take root, and that means that markets need to become much more connected. And as I showed you as well, there are a few underlying challenges having to do with resources, storage and energy storage, in particular also hydrogen, for example, CO2, agricultural optimization I briefly touched upon. And as I started my talk with, the need to really build efficient hydrogen systems is paramount or imperative to go way beyond, say, just hydrogen as a fuel. And indeed, other routes to clean hydrogen may need to become very relevant and should be studied much more, because there may in fact be societies that would opt for these solutions to a degree. Maybe not ours, I'm not sure, but maybe also ours. I find it very interesting that, for example, in the Dutch society, the word nuclear is sometimes heard again. And with that, I'd like to conclude and thank you very much for listening.
Thank you very much, Dirk. Fascinating talk as always, and generated lots of questions, and I'll try to get to a few of those. I'll start with a question. Hydrogen was an interesting piece of your presentation. I want to start there with a question about the transport and storage of hydrogen. I mean, if that's going to be an important vector in a net zero system, what do we need by means of transport and storage, and how do you see the challenges or opportunities there?
Well, the easiest, and I would argue that's probably also where most people look at right now, is to build hydrogen from, or to produce hydrogen from methane in a methane reforming process, where you capture the CO2 at very high percentage, much higher than the capturing technologies that I mentioned here. You can do that. Shell has a proprietary technology for that. And in fact, transport it then, as well as store the CO2 that you create in this process into the subsurface. For that, there are, of course, options to transport it by truck or by train. I think that most likely we'll see that gas grids uses will be reused and made suitable for transporting hydrogen. For example, there are discussions here in Northwest Europe to do that, and that doesn't seem to be too outlandish. It is true that you cannot just, of course, assume that hydrogen will be as effectively transported through pipelining systems. And maybe if those grids are not there, that large railway connections indeed would use, and then indeed trucking, say, hydrogen. I would be cautioned by assuming that you can do everywhere CCS. I don't believe that. Many people would like to do the CCS perhaps close to where you would use the hydrogen. But I doubt that. I think there's such an enormous scale needed for that you probably will only see that accepted in societies once there is already a culture and a awareness and a history of, for example, large-scale hydrocarbon businesses. So it is indeed advantages in transport through pipelining. It is in probably scaling up blue hydrogen initially, but ultimately these things need to be green. And I think we shouldn't be under any illusion that at some point, hopefully sooner than later, large-scale green power or green routes to zero carbon hydrogen are important. I'm not so convinced that will always be solar and wind.
Okay, so you mentioned nuclear as one of your high power density targets. Going forward, there's been a lot of pushback societally. You just alluded to that. Yeah. What are your thoughts on fusion? Well, a different approach, not there commercially yet, but certainly the targets are for exactly commercial.
The point. I would love to see fusion happening soon. Because ultimately that is probably nature's preferred way to make zero carbon energy. It happens at a very large scale, much larger than we need. And fortunately, it's not so conducive for human life in the way that it is produced today at great distances from us. I would argue that, for example, what Dennis White is doing at MIT, it looks very promising. It's a combination of breakthroughs in material science as well as novel concepts. And for those that are familiar with that, I think the way they essentially create or produce materials to do these to create high density magnetic fields is actually very, very attractive. And I hope that test that I think is happening in 1 or 2 years would indeed be successful. However, it probably will still be a long way before these things will become commercially available. So I do think societies like advanced societies like the US and Europe should pay more attention and pay more put more efforts in to build commercial routes to nuclear fusion. But it is still quite a long way out. Paris needs to be done by 2050. So it's not really a solution in the next 30 years at scale. I don't think so.
So let me ask a question about low density renewables, low energy and power density renewables, and contrast that with food production, which is also requires significant amounts of area. And yet we very successfully, harvest the food products and aggregate that and move it to large urban areas. And we do that with electricity today. We have a large, not big enough for the renewables we would need, but a large aggregation system and transmission, so distribution system. What do you see as the limitations there that drive you to focus on the high power density energy production?
Well, two things. I would actually dispute whether we are very good in agricultural densification. Yes, we are very good in the Midwest, perhaps in the US, and maybe in Europe. We're not very good at that in Asia, in India, or in Western China, or closer to the big cities in China at the moment, in Eastern China, where a lot of sustenance farming is still happening, where a lot of farming with live animals is happening, not for production, but for work, which actually is a significant greenhouse gas emission factor. And in all things, the actual distribution system for food into cities is not very good. Even for a city as Mumbai, the actual production of almost a national fruit, I think, the mango, say a few hundred kilometers from Mumbai, changes 40 times hands before it actually hits a market in Mumbai. These things don't stand on its own. These things don't happen in isolation. The whole agricultural system and the supply of food needs probably to become a lot more efficient and denser with less area assumed. So I think that, and that is even true, even more so, if the population starts to grow. And it starts to grow, as I showed you, in Asia, first and foremost, and then later on in Africa. So what I would argue is that people in the middle class would also like to have probably a similar type of diet as we have here in the West, which requires more energy and more preparation time, and probably also more land to create. I didn't do that sum, so I would stand corrected there perhaps. And what I do know is that the World Resource Institute projects that if nothing changes, then we need twice the total land area of India to be devoted to just crop growth to feed 10 billion people. And that land isn't there. So rather than perhaps banking on yet another Haber-Bosch, I think where the trick now will be is to essentially see whether we can upgrade or intensify agriculture by soil improvements. Maybe that was also behind what Haber-Bosch did, but a lot more nuanced this time, not destroying, say, biodiversity, because if anything has come out maybe quite recently, is that biodiversity is key to actually make sure that for a longer period of time, you can expect significant growth in crop yield. But these things are possible. The same institutes that put out those numbers also show that there are biochemical and biological engineering pathways based on CRISPR technologies and based on new chemical materials that come mostly out of the biochemical industry, and lo and behold, can actually be made with small molecules that are someone else's waste. That doesn't happen yet. And so I'm not saying here that, look, I mean, it's pretty obvious, this is what you need to do. But I am, in that sense, indeed quite an optimist, having seen what actually is possible today, holds great promise. Also, because we will have to. If we are to decarbonize heavy industries in Asia, steel, cement, ammonia, polyethylene, and essentially get them off coal, and maybe also eventually from natural gas, then we will have to create, that will take time because of the enormous growth that these manufacturing industries need to supply. Against the growth, therefore, it is probably a very wise strategy to help at least to decarbonize by not changing the fuel immediately, but essentially mitigate against the adverse consequences of having still these heavy industries run on, say, coal or natural gas. Again, that's not meant as making a hydrocarbon industries prolonging. It's simply probably a reality that there's not enough budget or not enough effort possible to actually decarbonize faster than the population demands goods from these industries. So for that time being, dealing with waste streams and dealing with a degree of circularity made possible perhaps by advanced chemical or biochemical manufacturing techniques, similarly, well, not so similar, I would say, but certainly in replacing perhaps some part of the petrochemical industries, which is definitely happening. Small startups start to do this. And this is in the interest of big energy companies. And that's why I mentioned that, because these connects may actually mean new markets. And new markets are important. They may not be the old known markets or just the old known markets that we know today in transport and parts of industry, perhaps.
Good. So the final question, and you can answer or not. This gets back to the introductory comments about the Shell's release. But let me ask, will Shell be publishing quantitative targets for Shell for 2030, 2040 on its path to net zero in 2050?
Well, to be absolutely honest, Bob, I don't know.
Yeah. Okay.
For two reasons. One is I don't think we have those targets worked out definitely without any shred of doubt.
Yeah.
In other words, there are people who do these calculations, and then of course a lot of other calculations happen, and you know how that goes in a big company. So I don't think that has landed yet exactly what that pathway will need to be. Another thing is that because that isn't happening, I don't know really what would be truly business competitive in that sense, and you will never disclose this, versus what you better disclose because you need a lot of collaboration and alignment with government policies, etc. So from that point of view, fundamentally, I don't think Shell will hold back any of its targets. But it is against these two facts, one, that we may still be in a process to figure out, well, how do we actually get to 2035 with these targets? I don't think the last word is said on that. I'm not aware, at least, that there is a clear blueprint available. It's something that is being built, and what would then make sense to disclose will probably be very much, of course, looked upon. Well, what does this mean for our future competitive markets and competitive position in new markets and growing, say, like these things I just mentioned, for example, in Asia.
Sure.
And that's an ongoing process. But fundamentally, given the nature that a lot of technology and a lot of collaboration is done jointly with different client groups in a customer-centric way, as I explained, that actually is very conducive, or it's very natural then to expect that you also become very explicit about what these targets are. So I haven't come across in Shell that, oh, no, we say one thing and we hope that it will go away and can continue until 2050, and they can say, well, look, yeah, maybe it wasn't a bit too ambitious, but hey, there's still a lot of hydrocarbons to be produced from, and we will still be able to service you. That is not an attitude that I see in Shell at all. It is difficult to see how to scale up actions in a profitable enterprise, for sure. So that's not without its own challenges. But I'd like to come back to this question perhaps in my next talk.
Yeah, no, that would be fine. And it wasn't meant as an adversarial question. It was meant to.
This is still a benign question.
Yeah,
I was
no. So let me thank you once again, Dirk, for really interesting talk, as always. Lots of insight into the energy system, a lot of quantitative thinking about the impacts of different technology options and what we may or may not be able to do, and what the challenges are and opportunities for getting there. So uh, deeply appreciate your willingness to share that and have this conversation with the MIT community, which I am sure will continue on as we continue our work as a global society to get to net zero as fast as possible.
Yeah, well, thank you very much, Bob, for the opportunity and for the MIT community to have me here. I'd like to come back. Maybe if there are indeed still quite a lot of questions that I couldn't answer, you can send them to me, and I could see what answers I could be able to give in a reasonable time frame to use. So I'm not walking away from the questions that were not surfaced.
No. It's good. Thanks very much.
Thank you very much.
Just as we wrap up, I just wanted to point out that upcoming, we have on February 24th at 10 a.m. Boston time, a webinar workshop on decarbonizing buildings that'll be co-presented by MITI and MIT's Industrial Liaison Program. And I encourage all of our listeners to look at the MIT Energy Initiative events page for lots of other upcoming events. So once again, thanks, Dirk, and thanks for everyone who tuned in and asked a set of great questions. I'll see you again at a future event. Thanks.
Thank you very much.
Okay.
Thanks.
Thank you.
Bye-bye.
Goodbye.